time travel, the very idea sparks our imagination. From H.G. Wells's The Time Machine to the adventures of Doctor Who, we've been captivated by the possibility of journeying through time. But is time travel just a fantasy, or could it one day become a reality? Scientists are exploring the mysteries of time, searching for answers in the fabric of the universe itself. While we haven't quite cracked the code, the journey of discovery is just as thrilling. For centuries, time was seen as a river, flowing in one direction. Then came Albert Einstein, who revolutionized our understanding of time with his theory of relativity. Suddenly, time wasn't a rigid, unchanging entity, but a flexible part of the cosmos, intertwined with space. This idea, known as spacetime, forms the basis of our modern understanding of the universe. The quest to understand time travel isn't just about satisfying our curiosity. It has the potential to reshape our understanding of history, the universe, and our place within it. Imagine witnessing historical events firsthand, or traveling to the distant future. Time travel, if achievable, would hold profound implications for humanity and our perception of reality. While we haven't built a time machine yet, the journey of exploration itself is pushing the boundaries of human knowledge. As we delve deeper into the mysteries of the universe, the possibility of time travel, once confined to the realm of science fiction, is slowly inching its way towards the realm of scientific inquiry. Imagine a vast, four-dimensional fabric. This is spacetime, the fabric of the universe according to Albert Einstein's groundbreaking theory of relativity. In this fabric, space and time are interwoven, no longer separate entities. They can be stretched and warped, much like a trampoline bends under the weight of an object. One of the most mind-boggling aspects of Einstein's theory is that gravity isn't just a force, but a curvature in space-time. Massive objects like stars and planets create dips in this fabric, causing other objects to be drawn towards them. This is what we experience as gravity. This warping of space-time also affects time itself. Time slows down near massive objects. This phenomenon, known as time dilation, has been experimentally verified. Clocks on satellites, for instance, tick slightly faster than their counterparts on Earth due to the difference in gravity. Einstein's theory of relativity completely changed our understanding of space and time, and it laid the foundation for exploring the possibilities of time travel. If space-time can be warped and stretched, could we potentially manipulate it to journey through time? The quest to understand time travel takes us deep into the heart of Einstein's universe, a universe where the seemingly impossible becomes a tantalizing possibility. It's a universe where the boundaries of space and time blur, and the very nature of reality is up for grabs. Imagine folding a piece of paper in half and poking a hole through it. This simple act creates a shortcut between two distant points on the paper. This is a simplified analogy for a wormhole, a theoretical tunnel that could connect distant points in space-time. Wormholes, predicted by Einstein's theory of relativity, are like tunnels through the fabric of space-time. Theoretically, a wormhole could allow us to travel vast distances across the universe, or even jump to different points in time. They offer a tantalizing possibility for interstellar travel and potentially time travel. However, wormholes remain highly theoretical. For one, their existence hasn't been definitively proven. Even if they exist, they are thought to be incredibly unstable and might collapse before anything could travel through them. Scientists have proposed various theories on how to keep wormholes open long enough for travel, such as using exotic matter with negative energy density. This concept, however, is purely theoretical and presents its own set of challenges. While wormholes offer a captivating glimpse into the potential of time travel, much more research is needed before we can consider them viable portals for traversing the vast expanse of space-time. One of the most intriguing aspects of Einstein's theory of relativity is the concept of time dilation. It states that time doesn't flow at a constant rate, but can be influenced by gravity and speed. As mentioned earlier, time slows down near massive objects due to the warping of space-time. This effect, known as gravitational time dilation, has been observed in experiments and has practical applications, such as in GPS technology. Time dilation also occurs due to speed. The faster an object travels, the slower time passes for that object relative to a stationary observer. This is known as velocity time dilation. The effects of time dilation have been observed in experiments with atomic clocks flown on high-speed jets. The clocks on the jets ticked slightly slower than synchronized clocks on the ground. Astronauts on board the International Space Station also experience time dilation, albeit on a much smaller scale. They age slightly slower than people on Earth due to their high speed and lower gravity environment. While the time differences experienced in these examples are minuscule, they provide concrete evidence for Einstein's theory of relativity and highlight the flexible nature of time. Time travel, while fascinating, is riddled with paradoxes that challenge our understanding of cause and effect. One of the most famous is the grandfather paradox. Imagine traveling back in time and accidentally killing your grandfather before your parent was born. This action would create a paradox. If your grandfather died, you wouldn't exist. But if you don't exist, how could you have traveled back in time to kill your grandfather in the first place? Such paradoxes raise questions about the consistency of timelines and the possibility of altering the past. If time travel is possible, how do we reconcile it with our understanding of causality? Some theories suggest that any attempt to change the past would be impossible, as the universe would somehow self-correct to prevent paradoxes. Others propose that time travel might not allow for changing the past, but instead lead to branching timelines or parallel universes. The concept of parallel universes, often found in science fiction, offers a possible solution to the paradoxes of time travel. Imagine a multiverse where an infinite number of universes exist, each representing a different outcome of every possible event. In this scenario, time travel might not be about changing the past in our universe, but rather about accessing different timelines or parallel universes where alternative versions of events have unfolded. For instance, if you traveled back in time and prevented your grandfather's death, you might be shifting to a parallel universe where that event occurred, creating a new timeline separate from your original one. The idea of parallel universes is highly speculative, but it offers a fascinating framework for exploring the possibilities and consequences of time travel without violating the laws of physics as we understand them. While time travel remains largely in the realm of theory, the pursuit of understanding time's mysteries continues to captivate scientists and fuel our imaginations. Whether or not we crack the code of time travel, the journey itself is pushing the boundaries of human knowledge. Advances in physics, particularly in our understanding of quantum mechanics and the nature of spacetime, could one day provide us with the tools to manipulate time in ways we can only dream of today. However, time travel, if achievable, would come with immense responsibility. The ability to traverse time could have profound implications for our understanding of history, the universe, and our place within it. The quest to understand time travel is ultimately a quest to understand ourselves and our place in the cosmos. It's a journey filled with wonder, possibility, and the constant reminder that the universe is far stranger and more wondrous than we can imagine.